Let's start with a prayer. Any volunteers to offer a prayer for us?
I can say it.
Thanks, Isaac.
Heavenly Father, thank you for this day. Thank you for this opportunity to be here on Zoom, for the opportunity for the technology that we have to meet and study even in the midst of the pandemic. We thank thee for the preparation that Brother Corey has prepared for this lesson, and for especially for all his classes throughout this whole semester that have prepared us for this final. It is blessed that we may study hard this next week, and that we may succeed to the best of our abilities in all our finals, and especially today that we may succeed in studying for this our math final. And say this in the name of Jesus Christ, amen.
Amen. Thank you so much, Isaac. So the final exam, we will try to have it sent out or have it start on Saturday, first day of finals, and you'll have either the full week or one day less than the full week to finish. We're still working on that. The way it looks now, I wouldn't be surprised if it's the full week. It's on Gradescope, same setup as the other exams. You'll be on your honor to take it under testing center conditions. No use of phone or notes or textbook or anything like that, or computer looking up information. You can use your phone, of course, to take pictures of the homeworks that you need to upload for Gradescope. I mean, not homeworks, but pictures of the free response problems to upload.
Is there a time limit?
There'll be a very, I don't know what the right word is, but lenient time limit. Yeah. So usually you have 3 hours time limit on final exams, but I think it'll be like the other ones, just a time limit to make sure you just do it in one sitting and that you don't spend more time than is useful for you on it. So, okay. Any other questions? Okay, so I'll tell you what's on the final exam. But what I did the analysis I did to tell you what on the final exam is actually one that you could have done. All I did was look on the 4 practice finals that we have put up there and started looking at what was on every exam or almost every exam. So I did that, and I wrote up a final review sheet. And this is on Learning Suite. So if you go to the content page where the old practice finals and the keys are, then this is just above those. So this is a final review sheet just based off of other things that have been asked about on the past finals. So so this is a good strategy, a nice strategy if you have access to old finals or old midterms in other classes too, not just this class or math classes, is start looking and see what do they ask all of the time, and that's a good place to start for your review. So the last problem on every single one of these exams is find the single value decomposition of a matrix. So if I were you, I'd make sure you'd know how to find the single value decomposition of a matrix. It's been asked every time in the last on these practice exams and the last finals or the last year. It's probably going to be asked again. No guarantee, but that seems like it's something that the professors are emphasizing, so you should know how to do that. Orthogonally, every one of those exams asks to orthogonally diagonalize a matrix. So you should know that you can orthogonally diagonalize a symmetric matrix, and all matrices that you can orthogonally diagonalize are symmetric matrices. So if you know it's symmetric, you know you can orthogonally diagonalize it. If you know you can orthogonally diagonalize it, you know it's symmetric. Every one of these asks to find a basis for W perp, given the basis vectors for W. Every one of them asks about an orthogonal projection of a vector Y onto a subspace, usually given vectors, basis vectors for the subspace. Sometimes they'll ask for the perpendicular component of the projection and not the projection itself. So every single one of these asks, they describe a linear transformation, and they ask for you to write down the matrix that corresponds to that linear transformation. All these were 2x2 matrices with transformations in the plane, like rotate it clockwise 45 degrees and then stretch by 2 or so, by a factor of 2, something like that. Every one of these asks to find the inverse of a matrix that's larger than 2x2. So make sure you know how to do that. 3 of the 4 asks for something about using Gram-Schmidt orthogonalization to create an orthogonal set of vectors. So you should know how to do that. Either had to find the determinant of a matrix or use properties of determinants to find the determinant of a matrix that wasn't given. So you should make sure you know that. These are, I should have mentioned before, I split things up on this review sheet. These are things you should be able to know how to do, but also there are things you should understand, okay? Where there are questions that they're not going to ask you to do something, but they're testing to see how much you know, what you understand about the properties and the theorems and the relationship, et cetera, the concepts, the key concepts that we've been working on. And these past exams are heavy on the stuff later in the semester. And so, the list here is kind of heavy on the stuff later in the semester. Doesn't mean that earlier stuff isn't on there. It's just not emphasized as much. So solve a matrix equation for a given matrix. That actually I should put, that was actually, I think, only on 2 exams. So I should have put it down here in this section on where there were a few things that were on a couple exams, and I put them down here. They weren't emphasized as much. Find eigenvalues and eigenvectors of a given matrix. Those are usually in the context of doing other problems. You have to know it to do the singular value decomposition of a matrix or orthogonally diagonalize a matrix. Find the dimensions of the row space of A and the column space of A and the null space of A given the dimension and rank of A. So that was on every single, there was some problem like that on every single final exam. And then a few other things that were on some, like 2, find a basis for the 4 fundamental subspaces or a subset of those 4 fundamental subspaces. So given a matrix, can you find a basis for the row space of A, a basis for the column space of A basis for the null space of A, and a basis for the column space of A perp. So find coordinates with respect to a given basis. So that was on a couple. Find the diagonalization of a square matrix, if possible, and or use the diagonalization to find the power of a matrix. So these are kind of like big things you should be able to do. Big things you should understand. Often the questions that we use to ask about these are those check all that apply problems, right? Or true or false problems, those kind of things. So orthogonal matrices, we spend a bit of time understanding those and their properties. Symmetric matrices or matrices that are orthogonally diagonalizable, spend quite a bit of time on those. Invertible matrices, we've learned a bit more about invertible matrices since the last exam. Eigenvalues and eigenvectors, like understanding their properties and their definitions and such. Diagonalization of matrices and their connection to algebraic and geometric multiplicities of eigenvalues and linearly independent eigenvectors, like the connection with all those. And then stuff from earlier in the semester with just solutions to a system of AX equals B if you know something about A, how does it impact the solution to that system? Like if A is invertible, what do you know? If A is not invertible, what do you know? If A is not square, what do you know? Stuff like that. And properties of matrix vector operations. So being able to solve equations for matrix equations for a given matrix represented by X, for example. Well, that's something that that's something that you do, but understanding the operations and the properties of like the transpose of a matrix and stuff like that. So, so again, this is up there. This is something that you guys could have sat down and done the analysis for and looked at what are the kinds of problems that are on every single one of these exams. And that tells you what, or on 3 of the 4, that tells you like where you should spend some time to studying to make sure you know that stuff, because it's probably going to come up again. So any questions about this or this document? Not necessarily about how to do one of these things, or questions about that. We'll get to that in a minute. But any questions with just what I've gone over so far?
This document's available on Learning Suite, is that right?
That's right. It's on the I think it's the practice exam page where the old finals are. So, okay, other questions? Okay. So, what I'd like you to do is go to the chat, and the chat from last class is still left up there, so I didn't stop the call between classes. But go to the chat and type in the topics that are here on this list. They don't have to be on this list, but type in the things that you are uncomfortable with or things that you feel like you need more practice on. You can list more than one if you want. The kind of things that scare you on the final, like what kind of topics or questions you feel like you need more work with. So go ahead and list those on the chat. Okay. A few things while you're putting those up. Someone asked about TA office hours. Will they be the same today and tomorrow? Not necessarily. I was going to have TAs hold set office hours over finals week. If you have questions, just email them or me, and we'll set up a time to meet with you. There are a couple of review sessions set up. We haven't emailed them out yet. One will be tomorrow. So my office hours usually go 9:30 to 10:30. I will hold a review session 9:30 to 11. There is a math lab sponsored review session that's also, it's 9 to 11 tomorrow. So I already had committed to do mine, and then I found out they had theirs, so they were slow on getting theirs out. And then the TAs are holding one on Saturday, and it's Saturday 2 to 4. We do have those review sessions coming up. I will send out an email. So you have all of those details for all those. Okay, so it looks like, so there's quite a few things here. So one quick one, the difference between diagonalization and orthogonal diagonalization. The process is similar, but diagonalization, so a square matrix might be diagonalized. You have the possibility of the square matrix being diagonalized. If it's a square symmetric matrix, then we actually know for sure it can be diagonalized, and that diagonalization ends up using the eigenvalues, the eigenvectors, and the eigenvectors are orthogonal to each other. So that's a key theorem that it's called the spectral theorem, is that for symmetric matrices, which all symmetric matrices are square. Like we call a square matrix symmetric if it's, we only call square matrices symmetric. If you have a symmetric matrix, then you can always diagonalize it, and the eigenvectors are always orthogonal to each other. If they have distinct eigenvalues, you're guaranteed they're orthogonal. If you have algebraic multiplicities of 2 or more, then you might have to do Gram-Schmidt to orthogonalize those that come in groups. But we can spend more time on that. I don't know if we'll get to it today. Several of you mentioned finding basis vectors for W perp or for the perpendicular complement. So that was something they wanted in the last class. So I actually have a problem set up, for a couple of these things. Okay, so here's 2 problems. This first one, this first one is a kind of problem that some of you have expressed you struggle with. These kind of problems where you mark all that apply, or the true or false stuff, it's stuff that you're not asked to do something. There's not a procedure. It's really about how well you understand the properties and how well you're able to use the properties and the theorems to reason through a given statement. So I wanted to do one of these. And then I do have this problem about finding a basis for W perp, which is one that you guys had mentioned. I'll try in the review session tomorrow to hit some of these other big ones, to be prepared to hit some of the other big ones that you've mentioned. So take a few minutes and think about these 2 problems and see how far you can get, and then we'll go through them as a class. So take, I don't know, 4 minutes or so to start on these. Well, take 4 minutes or so just on 2. If you finish 2, move to A. But I will give you some time, a few minutes to get ahead of me on the second problem too. Sorry, I said problem 2, but that's ambiguous. But when I say this 2, the second problem 2 is actually the first problem. So work on that first problem, which was called number 2. Okay, let's start talking through these. So this question asks about orthogonal matrix. So we just have a general orthogonal matrix. So if you're doing this problem on an exam, one thing you might start by, after you read that beginning, is just start writing down everything you know about an orthogonal matrix, or just reminding yourself about an orthogonal matrix. Like, okay, orthogonal matrices, what do I know? Oh, well, orthogonal means that their columns and the rows are orthonormal vectors, not just orthogonal to each other, but they're actually scaled. This is the one where the name doesn't quite fit the situation. So the columns and rows make orthonormal sets. Okay. What else do I know? And you can start listing off some of those things, you know, even before you start looking in at specifics. That might help to bring some things to mind, the things that you'll use as you go through here. So does U has n distinct eigenvalues? So is there any theorem about orthogonal matrices that says something about n distinct eigenvalues? Not that I remember. If you're in a situation like this on the exam, and one of the things you can do, instead of trying to think about it all in abstract, why don't you write down a few orthogonal matrices? Like the easiest one is the identity matrix. The identity matrix is an orthogonal matrix, and does it have, this is a 3 by 3, are there 3 distinct eigenvalues? No, there's only one eigenvalue. It's all there. The eigenvalue is 1 repeated 3 times. It's got an algebraic multiplicity of 3. So we've already found an example where that's not true. So we know that that's false. Okay. The columns of U are linearly independent. So you could start again by writing down a couple if you're not sure. We write down the identity matrix there, those columns are all independent. But the identity matrix isn't always the best one to use as an example because it has other specific nice properties. But why would the columns of U be linearly independent? If this was true, well, why? Well, the columns of U are orthogonal to each other. And orthogonal is stronger than linearly independent. It's like as independent as you can get. So so then the columns of U have to be independent because the columns are orthogonal to each other. So the dot products of all the columns are 0. So so they for sure are linearly independent. So that is true. How about every eigenvector of U has length 1? Well, the columns of U have length 1, but we don't know anything about the eigenvectors. In fact, an eigenvector can be scaled. So if we solved and the first representation of the eigenvector had length 1, we could double that or cut it in half or multiply by 10 or divide by a negative pi. Doesn't matter. It would still be an eigenvector. So we could change the length of the eigenvector. So that clearly doesn't have to be true. So that's false. Okay, how about the rank of A, which really should be the rank of U. So they had a typo on this one. So is the rank of U n? Well, if the columns of U are linearly independent, like we listed right here, then yeah, it's got to be true. Or if all of the columns are orthogonal to each other, then they're linearly independent. So so yeah, the rank would be n. The determinant of U is 1. We do know something about the determinant of U, the determinant of orthogonal matrices. Remember, we talked about the transformation of an orthogonal matrix. It maintains distances and angles, and it also would maintain areas and volumes. So if the determinant is tells you the factor by which areas get scaled, then it can't change that, but it could reverse some things. So the determinant of A, it could be 1, but it also could be a -1. There's 2 possibilities with orthogonal matrices. So it could be plus or -1. So that's false.
Wait, Professor.
Yeah.
So like, I guess I'm just struggling to interpret that specific, like the wording of that, because the determinant of U, like it could still be 1, right? So even though it doesn't also include -1, like couldn't it, does that make sense? Like it should,
Oh,
would it
so
still be, would not be true?
right. So in mathematics, we only say things are true if they are always true. So so it could be 1, but it also could be -1. So since it's not always, the determinant of an orthogonal matrix is not always 1, we would say it's false. So in mathematics, for something to be true, it has to always be true. So
Okay.
I'm glad you raised that. Yeah, I think that actually tripped up some people on the last exam also with some of the true false things. So another strategy here is you could start listing off some matrices, some orthogonal matrices. Like even as simple as this, those are 2 pretty simple ones, and the determinant of the first is 1 and the determinant of the second one is a -1. So so that's one way to show that it's false. Okay. So U transpose U is the identity matrix. Yes, that's one of the most fundamental things that we've learned about orthogonal matrices, is that the inverse of an orthogonal matrix is the transpose of itself. Yeah, it's the transpose. So, yep. And how about the next one? U times X dot U times Y equals X dot Y. This is a line from a theorem in the book, but if you're on the exam and you're not sure, you don't remember that, you could think about what you know about UX or UY. So you could think like, this is U is transforming X, U is transforming Y. I know something about the transformations of U, that U can't, U won't change distance and U won't change angles. And X dot Y is related to the angle between those. So since it doesn't change angles, it makes me think like that Ux dot Uy probably should be the same as X dot Y. So I'd be inclined to say true there. Because of that reasoning, you could also try an example. This is a place where I wouldn't pick the identity matrix to try an example. Maybe pick something like 1 over the square root of 2, 1 over the square root of 2, negative 1 over the square root of 2, 1 over the square root of 2. This is an orthogonal matrix that we bumped into quite a lot. It comes up in simple examples of singular value decomposition quite a bit. So pick a U, and then pick 2 random X's and Y's, -3 and 10. And so let's have that be X, and then pick a Y, and I don't know, 1/2 and 5. I don't know. Pick 2 random things, and then you can do the math, see if it works out. Like that hopefully can help you lean one way or the other on whether it's true or not. So you can find the dot product of X and Y, multiply them both by U, find the dot product of those. You can also think about using properties. If you remember that U transpose U is the identity, you might think, hey, can I use that somehow here? So we've done a few other times, we've rewritten dot products as matrix products with transpose. So I could rewrite UX dot UY as UX transpose times UY, where it's just a matrix product. And then that is X transpose U transpose UY, and that is X transpose Y, because that simplifies the identity matrix, and that is the same as X dot Y. So here you can reason through using properties and manipulation, and we just proved that that's the case. So I know not all of you, I wouldn't have been comfortable doing that. I wouldn't have known enough to do that, but I know some of you are. So, so yeah, so that's true. U has orthonormal columns. That is the definition of an orthogonal matrix, pretty much. So yes, that's true. So, okay.
Professor, on the final with questions like this, will we be awarded points per box, or do you have to get every single box answer correctly to get points for that question?
It's points per box. So like on the last exam, it was a point per box on these problems, and then the multiple choice where there was just one answer, I think was 4 points per question. So.
Okay, thank you.
You're welcome. Okay, any other questions on this problem or these kind of problems?
Just on that proof, is it always the case that like that a vector dot a vector is equal to the first vector transpose times a vector without like being dot product, just normal?
Yes. Yeah. So that's unless otherwise specified, we write out the vectors longhand. We write them down as column vectors. So you have to specify otherwise if they're not. And once you transpose one, so if we don't think of it as a dot product and we transpose it, then it becomes this. And then you have all of this times all of that, and it ends up being the exact same thing when you do the algorithm. So
Nice.
Okay, good question. Other questions? Okay, so go ahead and start working on this second problem then. So we have two vectors in R4, and we want to use this to find a basis for W perp. Just a clarification, this is a perfect example of what someone just asked about. These have transpose because it's easier to write the vectors when you're just writing in a line, save space to just write them that way, but they have to write transpose so it's clear that, hey, they're really talking about this vector here, not the 1, 1, 0, 1 sideways vector. So that's why they write the transpose there.
About that, I've always wondered, like, sometimes when we're not about this, but about like when we're doing row space, I've seen like some places they write it as like a sideways row vector, but some places they end up writing it as like an upright vector, like a normal one. Does it, in that case, does it matter which way you write it when you're asked for the row space?
I always write them as, if they're row spaces, then I always write them and write them like they look like a row, that it's clear that it's that, that way. But I don't know if there's a standard way or not. Well, there obviously isn't a standard way because you've seen those, but because you've seen it both ways. But yeah, I always write my row vectors as long, thin. I mean, like they're,
Yeah, that
I
makes
always
sense.
write them horizontally. So
Yeah, that makes sense.
yeah. Okay. So go ahead, take a couple minutes, work on this problem. Okay, so I'm going to start talking through this. Make sure we can get through this before we run out of time. So one of the key things about finding a basis for WPERP is understanding how to do that. And the key thing here is that finding a basis for WPERP is the same thing as finding the null space of A transpose. So if you set up your vectors in a matrix, but there's two different ways of setting up the vectors in the matrix. So this is actually key in this problem, understanding these are transpose vectors. So your matrix A would be 1, 1, 0, minus 1, and 0, 0, 1, 4. So so that's our matrix A if we put those vectors into a matrix. And I want the null space of A transpose, so I transpose those, augment it with 0, and then row reduce. But I'm sure some of you would struggle or think like, hey, I'm going to, or just by default, just start finding the null space of A and not do the transpose. But here's some good ways to think about why you want to do the transpose. I'm in R4, so I need 2 more vectors. Well, at least 2 more vectors if these are linearly independent, and they are linearly independent because they're not, I only have 2 of them, and they're not scalar multiples of each other. And so the basis for what I'm looking for, it's going to need 2 vectors, and they have to have the same number of entries. So at the end, I need to say, oh, a basis for WPERP, it's going to look like this. And I have to have the points or vectors in the same, that live in the same world, that live in R4. So I need to have 4 entries here. And if I need 4 entries in each of these, that means I need 1 for each variable. That means I need 4 variables. And if I transpose the matrix A, I get 4 variables. If I don't and just treat it with A, I only get 2, X and Y, or X1 and X2. So, so just using my understanding of what WPERP is and reasoning about dimensions, then there's only one option I have here, which is the only hope I have of getting 4 variables is if by looking at A transpose, because my vectors have to live in R4. So that's the kind of reasoning that you can do when you're stuck on exams, using some of your reasoning, some things that you know to help reason through things that you might not know or might not remember. So okay, so this is already in row reduced echelon form. That's really nice that they gave us this. I've got a pivot column right here and a pivot column right here. It's as far as I can go. So I'm going to translate that into variables. So x1 plus x2 minus x4 equals 0. I could show that, I could specify that these 2 are free variables. So x2 and x4 are free variables. And x3 plus 4x4 equals 0. And I do know that x2 equals 0, x4 equals 0. Ah, not 0. They're free variables. They equal themselves. They equal whatever they equal. So, and now I can use those and take all my x2s and x4s, pull them to the right-hand side, see what I get. So x1 equals a negative x2 plus x4. x3, well, let me do x2. x2 equals, it's a free variable, so it equals x2. x3 equals a negative 4x4 x4 and x5. Oh, silly. X4 is a free variable. It equals x4. So now I can take the coefficients of each of these to create my variables or my vectors. So a -1, 1, 0, 0, and 1, 0, a -4, 1. So these are my basis vectors for W perp. Okay. Questions about that problem? Looks like someone that asked on the chat, how do you know that x2 and x4 are free variables? So any column that I have that does not have a pivot position, or any column that is not a pivot column, then the variable associated with that column is a free variable. So that's how I know, because my pivot positions are the first non-zero entries in each column. I'm sorry, in each row. Once I get it into reduced row echelon form. Once you get into row echelon form, but this is in reduced row echelon form. So the first non-zero entry in each row is your pivot position, and the columns that those are in are your pivot columns. So that's how I knew that x2 and x4 are free variables. Okay, other questions? Okay, great. I must be a great teacher or a really bad teacher. Either so confused you don't know what to ask, or you understand it. So,
I have a couple, just like they're probably pretty easy to answer, but on the last midterm, there was like some notation when with the questions involving like whether something was a subspace or not. And I was wondering if you could tell us more about like some of those notations, because I wasn't really sure how to interpret some of those.
okay, let me pull up that exam really fast. Okay, so question 3. So for each part, determine whether a given subset is a subspace of R3. Okay.
Could you share your screen?
Yeah, well, I was just going to write them down, but I can share my screen too, or pull it over here. In Gradescope, it splits the screen. And it's not super easy. Oh, come on. Oh, there it comes. Okay. So here's the problem I think that you're talking about, question 3. So each of these, so you're talking about like this kind of, it's called set builder notation.
Yeah, I wasn't sure how to interpret some of these. Some of them I got, but some of them I was like, I don't know what this means.
Okay, so I'm just going to pull out my annotation tools here. So so this gives some criteria, and this gives other information. And the way you read this is the set of all these where T is this. So so this is like shorthand for writing down a really big set. We couldn't write down all possible entries in there. We couldn't, we could write 1, 3 square root of 1. That's one of those, but also is 2, 6, and the square root of 2, and also 0, 0, 0, is in there. Like there's infinitely many things, and for any t we could plug in there, there's infinitely many. So this is a shorthand notation of writing all of that set. So so for any t and r, we plug into this formula, or this vector, this parameterized vector, and we get something out, and it's those things that we're dealing with. So
okay, that makes sense. And so in this case, like it's not a subspace because that's not just a line, because as t increases, like it doesn't change linearly with that bottom value there, the square root of t.
that's right. Yep, that's right.
Okay. Could we look at like the next two, because they're a little different too, if I remember right.
So here, so this says x is in R3. So x is going to be a vector. Oops, I got rid of my notations. Hold on. So it's just going to be it's just telling you it's a three-dimensional vector. So x is in R3, and you have ax equals 0. So you have some vector times x, and some matrix times a three-dimensional vector equals 0. And is this a subspace or not? And here you have very little to go on. This is a problem I think everyone got right, because there was some information that was missing about the dimension of A. So we gave everyone credit whether you wrote yes or no on this problem. I think originally it said it's a 2x3 matrix. A is a 2x3 matrix. And so so in that case, you can reason through whether it's a start to reason through whether it's a subspace or not. But one of the ones that people missed the most was this next one. Yeah, down here. So this is one of the hardest problems on the exam. So this is all of the three-dimensional vectors x, where you can multiply by a and get 1, 2. So your subspace are these x things. Like you have something that looks like these 3 entries, and you get out 1, 2. Well,
so a would have to be 2x3.
Right. So then you can reason through what size a would have to be to have that happen. And then you could start to reason through whether it's a subspace or not. The easiest argument to say that's not a subspace here is that the vector 0, if x is the 0 vector, oh, that's bad. If x is the 0 vector, then you have to get 0, 0 out. And so, but the 0 vector has to be part of your subspace. It has to be part of your set for it to be a subspace. So since 0 isn't in that set, you know for sure it's not a subspace. So there's other ways to reason through this too, but we're out of time right now. So, okay.
Yeah, that was helpful. Thank you.
You're welcome. Thanks for asking that question. Okay, good luck, you guys. I know I'll see some of you tomorrow at the review session. Mine will be 9:30 to 11. Come with questions, and we'll work through more problems and talk about things and try to build understanding and get you ready for the final exam. Study hard. Make sure you go through all those. Make sure you go through all of those old finals, and make sure you catch up on the things from that trip you up on the previous midterms. So
Thank you.
okay. Thank you, everybody.
Thank you.
You're welcome. It's great to have you all in class. So, good luck.